Hi everyone, I'm Nadim Saeed. I'm a quantum photonics researcher here at EigenQ, and today we're going to be talking about quantum random number generation and showing two experiments that demonstrates how that phenomena is really quantum. Just a little bit about a pseudo-random number generator and how it differs from a quantum one. A pseudo-random number generator uses an equation and an iterative process with an unknown that is very prone to attacks or breaches from hackers. If an attacker or a hacker finds the unknown, they can breach the system and figure out the next possible outcome of the encryption. Now, I'm going to show you this experiment, which is called the Michelson Interferometer, and this really shows how a quantum random number generator works based on photonic technology. So inside our quantum random number generator, we have a laser diode and a photon counter. The laser diode emits photons, which are light particles, and the photon counter counts the number of particles coming out of the laser per unit time. That number is completely random by the nature of quantum mechanics, and the best we can do is model it using Poissonian statistics and just say in the rough likelihood where the photon or how many photons we're going to have per unit time. There is no way to actually find the exact number, and hence we cannot breach the system, we cannot reproduce it or repeat it in any possible way. So just a little bit about the setup here. We have a laser diode, and we have a beam splitter, and we have two mirrors on each side. The 50-50 beam splitter is a half mirror, so it reflects half the light and transmits the other half. Both the beams shine back from the mirror, and they go to the beam splitter and through to the objective lens or a microscope. Now, the effect shown here is a quantum one at the beam splitter. We have no way of figuring out where the photon is going to go in the setup. The best we can do, like I mentioned previously, is model it through Poissonian statistics. The interference pattern shown here on the screen is showing and grounding the fact of wave-particle duality. So that is, light behaves as a particle and as a wave at the same time, and there is no way for us to know when it's behaving like a particle and when it's behaving like a wave. This is a very ugly, chaotic, and noisy pattern shown on the screen, and this is exactly how EigenQ translates this chaos into number bits that computers can understand, such that we can encrypt keys and do many different stuff with encrypting data on servers, computers, phones, tablets, you name it. Just a last piece here showing the interference pattern coming out of the objective lens. As you can see, the light and dark fringes interfere here, and where we have light fringes, we have the peaks of waves adding up, and where we have dark fringes, we have the troughs and peak of waves canceling out, and hence we see this bullseye pattern, or an interference pattern is what we call it. Thank you very much. The second experiment is called the double-slit experiment. This was proposed in 1801 by Sir Thomas Young. And the way the experiment works is that a light beam shines into a diffraction grating where we get an interference pattern showing wave-particle duality on the screen. Here at EigenQ, we redesigned this experiment such that the laser beam shines into a crosswire shaped like an X, and so we see a different interference pattern on the screen, still grounding the same fact of wave-particle duality, however, showing that this interference pattern can move in 3 dimensions. And this is another explanation or visual understanding of how our QRNG at EigenQ works. It is a completely random and actually quantum random phenomena that we cannot predict what number we're going to get next, and hence prevents attackers or hackers from breaching the system. So the setup is very simple. We have a laser diode shining through an X crosswire filter, and then that produces a X interference pattern shown on the wall. We have light fringes and we have dark fringes, and if light behaved as a particle or as a wave, we would just see a regular dot on the wall. However, we see an interference pattern around that dot where we have light fringes and dark fringes. The light fringes are where the peaks of the waves add up together, and hence we get double the laser intensity, and the dark fringes is where we get the peaks of the waves and the troughs of the waves canceling out, and hence we see complete darkness. So just to show the interference pattern around the actual beam, there are many small laser fringes interfering in 3 dimensions around this main beam right here. So it's they're interfering around, and they show wave particle duality of this double slit experiment. Thank you very much.